iterate by parts to get zeta s is the integral from s times the integral from 1 to infinity, integral part of x dx over x to the s. And this is in sigma greater than 1, of course. X to the s plus 1. Okay, just integral by part. Now, one thing that we did before was, so we'll go to the equation number 6 in a second. So, in 7, replace x integral part of x by x minus fractional part of x. We did this before, and when you replace that, we end up with, and now the real story starts. Zeta s equal to s over s minus 1 times minus s. This is all familiar to you. Integral 1 to infinity, fractional part of x dx over x to the s plus 1. To begin with, in sigma greater than 1. But now we make the observation that the reason we needed sigma greater than 1 here is this is the order of magnitude x. So I want the denominator to be of order of magnitude 2 plus epsilon, so that the ratio is 1 plus epsilon to gain convergence. That's why I wanted sigma greater than 1. But now after having done this, and I pull out the pole at s equal to 1, this is bounded. Therefore, even though I started by saying this is valid at sigma greater than 1, it is indeed valid at sigma greater than 0. This was in fact something that was crucial in our proof, right? Indeed valid in sigma greater than 0. And why was this useful? Because the functional equation connects s to 1 minus s. So if you know only, if you know only in sigma greater than 1, 1 minus s is in sigma less than 0, you have got a gaping hole in between where you cannot make the connection. But therefore, simple as it is, you need to extend the Riemann zeta function of the sigma equal to 0, so that when I do the flip, it overlaps and you have the value of the Riemann zeta function defined in the entire complex plane by analytic continuation. So that is why, simple as it is, this is a useful step, a crucial step. Now, let's not worry about the functional equation. Can I use this sort of idea to get a further analytic continuation? Yeah, the answer is yes. So here's what we do. Next, so this is equation 8. Next in 8, replace fractional part of x by fractional part of x minus half plus half. The half is no problem. That's just going to come and give you an exact value. Now, what is the advantage of replacing fractional part of x by fractional part of x minus half? So let's look at a graph of this. So this is 0, this is 1, this is 2. Fractional part of x goes from minus half, minus this one, goes from minus half to plus half, which means when I start integrating, calculating the area, not only is this bounded, the antiderivative is bounded because this cancels this, this cancels this, this cancels this. So the property is, so this, okay, observe that the integral from a to b, whatever your a and b is, of the fractional part of x minus half dx is bounded. So not only is the function bounded, its integral is bounded. Whereas previously we only had a bounded function. So I subtract half, I get a function whose integral is bounded. So what does this mean? So this leads to, I'm going to give you the representation. So this leads to zeta s equal to 1 over s minus 1 plus 1/2 minus s times the integral from 1 to infinity fractional part of x minus half dx over x to the power s plus 1. That's all. All I've done is to replace this by minus half and add a half and calculate it. That's all I did. I didn't do anything fancy. Now, what is the advantage of 9? In 9, the integral of this is bounded. So this is like in Abel's summation a n bn by Abel's theorem. The sum of the a n is bounded. The bn's are decreasing and going to 0. Then a and bn is convergent. This is the integral analog of Abel's criterion. The integral of this is bounded. So all I need to know is 1 over this goes to 0. Then this will be convergent. But 1 over this will go to 0 as long as this is a positive power of x. Which means sigma greater than minus 1. So you can extend it to sigma greater than minus 1 by the integral analog of Abel's theorem. So let's write this down. So by the integral analog of Abel's criterion, nine provides an analytic continuation of zeta s to sigma greater than minus 1. By the way, this is not usually done in textbooks. I looked up a few textbooks and I couldn't find it. Zillions of textbooks on analytic number theory, so I might be missing something. So I'm just following on a lead given by my professor. He just mentioned this one day at lunch and he said, you know, you can do this. And so I just sat and gave this course on the Riemann zeta function. I said, let's try to work it out. Okay, so now I want to understand what is going on here. What is this half? This half is the average value of the fractional part of x between 0 and 1. That's what the half is. So that means when I subtract the half, the integral of fractional part of x minus half on this interval becomes 0. See, on a unit interval, the average value is the same as the integral. It's only in a non-unit interval you've got to divide by 1 over b minus a. On a regular interval, the average value of a function is just the integral on that function on a unit interval. Therefore, this half may be viewed in two ways, right? I mean, its actual average value, or if the integral of the fractional part function on 0, 1, that's a triangle, 1, 1 half. That's what you're doing here. So now what we have to do is, so I'm now going to introduce this function. Right? He didn't actually give me these steps, but it's not easy, it's not difficult to get this. So next what we do is, so we start iterating. So what is this iteration? I define f1 of x to be this fractional part of x minus half. Iteration begins here. And I define f2 star of t to be the integral of f1 of x dx from 0 to t. By the way, this is periodic. It's periodic because if I start integrating, I get some value, negative, 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 then it slowly becomes positive, 0. And I start again, so it's the same value. So this function is periodic, right? So f2 star, which is 0 to t, is periodic of period 1. That's why it's bounded. Okay, so it's periodic of period 1. Now, I define a new function, f2, define C2 to be the integral from 0 to 1 of f2 star of x dx. So this is like the average. So are you curious to know what this is? I worked it out for you during lunch. Okay, so f2 star of t is periodic, right, or period 1. So that means f2 star of t is the same as f2 star of the fractional part of t. So I can focus on 0, 1. Now on 0, 1, what is this? What is the formula for this? This is nothing but x, this fractional part of x, right? So it's x minus half from 0, 1. So the antiderivative of x minus half is x squared over 2 minus x over 2. So that's what f2 star is. So f2 star of x is x squared over 2 minus x over 2. on 0, 1. Otherwise you put fractional part of x. Don't worry, we are going to come to an end very soon. Only this much more space left. Okay, otherwise I can occasionally use that. But anyway, so that's what I tell my undergraduates. They know when the lecture will appear. Alright, so I have got this. Now what is the antiderivative of this object? So look at this integral. It's x cubed over 6 minus x squared over 4 between 0 and 1. These numbers are quite interesting. That's why I thought you'd be interested, because you're going to get Bernoulli numbers here. This is 1/6 minus 1/4, and that's minus 1/12. That's my constant C2. Now, that's the average of this function. This function doesn't have average 0. It has this as the average. It cannot have average 0 because the antiderivative starts out negative, 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 negative up to this point, then slowly positive, but it doesn't still, so it becomes 0 only at this end. So this function is always negative. And therefore its average is minus 1/12. Therefore, I now subtract f2 of t is now going to be f2 star of t minus this constant, which in this case is 1/12. Now if you want to draw the graph of this function, previously it was all negative and going again to 0, right? I mean, it was negative and then it becomes 0. It's sort of like this, with height 1/12. But you see, this cancellation is finer compared to this cancellation. So every time it's going to get flatter and flatter and flatter. So these functions are going to recursively define the sequence of functions. Okay. So that's what f2 star is. Now, why do I bring in f2 star? Because I'm now looking at this integral. That integral I now write as f1 of x dx over x to the s plus 1. And I integrate by parts, so I will use this form, sorry. Now when I integrate by parts, you always have a choice. You integrate one function, you differentiate another function. I will now integrate this function. Now when you integrate a function, you have an infinite number of antiderivatives to choose from. We say the antiderivative of x is x squared over 2, but you can make it x squared over 2 plus 5. So the antiderivative that I choose is not going to be f star, which is this integral, okay? But it is going to be the f star minus this constant, because the f star minus the constant has the property that when I integrate, this area cancels this area, that area cancels. So it's again one of these things where everything is bounded. Okay, so you integrate by parts by using f2 of x as the antiderivative. Which has the property. See, the reason I'm doing this is maybe one of you come up and say, sir, I have a new proof for the functional equation. That would be wonderful. You should immediately publish it in the American Mathematical Monthly. Right? I mean, you should think of these things, you always think of things in a new way. Simple, but novel way. Right, so it's an antiderivative which has the property that the integral from a to b of f2 of x dx is bounded. That's all I need, because when I integrate by parts, this integral now will be an x f2 have there, but divided by x to the s plus 2. But now you use the Abel criterion once more, and you only need s plus 2 to have a positive value for the convergence. So you now extend this to sigma greater than minus 2. And now we repeat the process. So this extends the Riemann zeta function. The half plane sigma greater than minus 2. Now, recursively, how do we define these functions? I'm going to give you the formula. Alright, so recursively define Fk star of x to be the integral from 1 to x, or Fk star of t, from 1 to t, Fk minus 1 of x dx. That's the first thing. And so this is going to be periodic of period 1. And now define Ck to be the integral of 0 to 1 Fk star of x dx. And then define Fk of x to be Fk star of x minus Ck. Same idea. But every time you'll get flatter and flatter. Maybe you'll get more. You'll get flatter and flatter. Because you see, you'll get ripples, because positive to negative to positive becoming 0, or increasing. Right? So it starts to, so it may have these ripples. I've not started graphing them. So each one will, so this will extend zeta s, so Fk will extend zeta s to sigma greater than minus k. You do this step by step. Now, I have not checked this.
Are those the
Like my statement on the Riemann zeta function, which led to a fruitful result that you proved. This should be equivalent to the formula for the Riemann zeta function that you get by using the Euler-Maclaurin sum formula. The Euler-Maclaurin sum formula involves Bernoulli polynomials and Bernoulli numbers. And this 1/12, I think, is again related. You have 1/2, 1/12, I think these are all related to the Bernoulli numbers. So it would be nice if one of you could show that this approach, so now I am Professor Strauss, my thesis advisor, just saying it's worthwhile. I'm not giving this as a homework problem, but to show that this approach is identical to the constants and other things that you get from the Euler-Maclaurin. Well, the final constants would be the same because there's only one analytic continuation. But would these be the same that you get from the Euler-Maclaurin sum form?
What about the Riemann zeta function guarantees that there's only one analytic?
There is only one, but you have to show that, you see, this is like Garvin's thing yesterday.
Yeah.
Right? I mean, he had one representation of Zagier's, he had another representation, and it's for the same function, but can you provide a transform which takes one representation together? That's a different
Yeah.
Well, so it might be more interesting if this gives you something that looks completely.
It's a different representation, but anyway, look at this in comparison with the Euler-Maclaurin sum formula. And Rademacher's book has the Euler-Maclaurin properties and Bernoulli numbers.
The only,
Chapter 1.
because like, aren't you only guaranteed that analytic continuations are unique up to poles?
No, even the analytic continuation is always unique. There's only
Okay.
one analytic continuation. If you expand, the coefficients of all should be identical.
Okay.
So there is no doubt that this is the same analytic continuation.
Okay.
But the point is there a connection between the way in which I obtain these values versus what you get from the Euler-Maclaurin? For example, let me just tell you, this is s over s minus 1. I mean, sometimes people write this as 1 plus 1 over s minus 1. There's another way of writing it, right? So ultimately that may have a different shape. But the question is, study the connections between this and the Euler-Maclaurin. I think it will be interesting. So because you have to study this Bernoulli, it's something that you are interested in. But others also, anybody here is welcome. This is open territory. Okay, so most probably, coming back for the last two classes, I will do the proof of Dirichlet's theorem on points and arithmetic progressions.